Hello, how's it going? Talk about regression today. A little bit of interpolation at the end. Regression is be able to relate an independent variable, here x, so you can choose whatever value you want of x, and you can have some data showing what happens to your y variable labeled y here, but it could be anything, any independent variable that's an outcome of changing an input variable. And here I just generated a linear relationship, y equals a half times x. X is an array of values from 0 to 10, and there's 100 points. And then I'm just going to space out this data, add some noise to it with my random number generator, and do that 100 times so it matches my 100 count x value here with 100 random numbers. I scaled it by a quarter. And here's what we have for data. So now we're going to try and fit a relationship to this to describe it. Of course, you'd expect it to be linear right there. So let's do that. So there's a number of ways to do that. Numpy polyfit. So you can use a polynomial. Numpy's polyfit package has a polynomial fit. Then there's Scipy's CurveFit and minimize. And we'll talk about those. Polyfit, yeah, you just call it and give it the data here and then the order of the polynomial. So here I've got x data, y data, and first order, and I can also change this to second order. And it didn't fit very well in the second order one. Does it do 0 fit? No, it doesn't do 0. So you have to do 1. You can do a third order. It doesn't do a very good job at all on that. But first order, it does. So it's a line. It's closest to a line. And here is that plotted for you. So it returns the parameters as an array. So here I reference them. The first one times x plus the second one. So that's the slope 0.493 and the intercept. Okay, well, how good is the fit? You've heard of the r squared value, hopefully. And it says number between 0 and 1. That kind of relates how well it's fit. And the closer to 1 it is, the better. I like that one. That's a good one. I like the mate value better, which is the mean absolute percent error, meaning, okay, if I use that relationship, how close to the actual answer could I expect to be on average? And it's the mate value, mean absolute percent error, and so you do just that. The error, then you take the absolute value and the mean of it and the percentage, multiply it by 100. So you take the difference in the data, that y is data and y hat is my estimate, and then I divide it by my data, so this gives you an error. Take the absolute value of that and take the average and times it by 100. So in this case, about 26% error on average by using the relationship. So that doesn't seem that good. Of course, it's because it's pretty noisy. And if I reduce the noise, let's come back up here. I can reduce my noise, change this number to like 0.1. You can see the noise goes down there. And that looks even better. So I had 0.967. Now I'm 0.99. And now I'm down to 12%. So those are things I'm going to ask you to do in your homework to calculate the errors for your fits. The next option is CurveFit. So in CurveFit, you could specify any linear or nonlinear relationship practically, or many of them, and you define it as a function. Here I've just defined a line, and then you use CurveFit, and you give the function you want it to fit to and your data, and it returns the slope and intercept, these parameters, and also the covariance or the uncertainty. And the slope is the same, 0.505 and negative 0.029. That's what we got up here, right here, 0.505, 0.029. And then the third method is instead of fitting to a curve, you're reducing the error. So you use your relationship, your line function, and you get a sum of squared errors. So here's my error, the actual minus the estimate, and I square it, and then sum up those errors. And then I try to minimize those errors with a guess value and give it the arguments of the data. So it sticks those arguments, x and y, right there. And if I do that, describe that, I get my slope and intercept. Your x's here are your parameters, these parameters. 0.0505 and 0.029, similar to what we got above. Okay, now let's use some real data. I pulled this data off of inthesky.org. We're just relating the sunrise time to the day for a given year. I got 2023 here. And so I've, sorry to skip around on you, just run these cells. So I wanted to plot day of year with the sunrise time. So if I knew a particular day of year it was, what time is the sun gonna rise? This doesn't look very good because the data doesn't come in as numbers in terms of the sunrise time. It comes in as, like, for instance, 9:14, 9:11, and so on. So I need to change that to a number. And let's just do a fraction of an hour from 0 to 24. Or actually 0 to 12, right? Yeah. So here, what I've got is, it's a string, so I'm converting this to a string first. Then I'm splitting it on the colon. We talked about split. And then applying a function to each of the values. And this is the lambda. So I take the split value, and the first number I just convert it to an integer. That would be 9. And then I add the second number after the split, which is, in this case right here, 11, divided by 60 to get it in hours, and then add it to that hours count. Another way to do this is to just create that function. So you're given a string, you split it on what comes in, and you're going to get an hour and a minute. And then you convert that here in the same way, add those two together, so you get an hour. Total hour count that includes the minutes as a fraction of an hour. And then we set a new column, sunrise hour, by applying that function line by line to that these numbers to get a new column with that function. These two things just do the same thing. Hoping you can get familiar with that for this apply. It's powerful. And then we're going to plot it, and you can see there it looks way better. Day of the year versus sunrise times. It's from 6 to 9 something. And now let's see if we can make a fit of that data. And I just came up with one, just said, oh, it looks like a cosine wave. Let me put in some numbers for cosine, and there we go. There's my estimate, but I didn't fit anything. Sometimes that can be very helpful when you have in a relationship you're not quite sure of, to like guess a function and then try it out. Just put some numbers in to see how close you can get. And it's a good way to do that, so you have a good guess values to start with. And here we've got our CurveFit. So I need to convert all this. I'm sorry, run all these cells. And here's our CurveFit. And so I've specified my cosine function with some modifiers here. And I've got an A, B, and C. And then I use CurveFit once again, put my function in and my data. Notice you don't have to have a guess value as far as your guess values for your parameters. You do on minimize though, and it spits these numbers out. And then I can plot that. Hey, that looks pretty close. Say I didn't want to have all these labels here. Say I just want to get rid of all this. It's too much to think about. And just have x plus b and c. Oh, it'll do the same thing, except doesn't. Why not? So that's what I'm talking about with having an estimate of what your function looks like to be able to have somewhat of an accurate expression. So this failed. This is not going well. So let's see. So I've got an A, and I need, what I think is happening is this B parameter. It needs my period for my cosine, because normally your cosine oscillates from 0 to 2 pi, right? But we don't want that. We want it from oscillating like over a long period. So this 365 kind of helps with that. So I divide 2 pi by 365, and that helps offset that, kind of lengthens that out. And yeah, so another way so it returns popped right here, and it returns an array. So I can also get my popped, it'll unpack it like with my decorator. Like for instance, if I just do cosine func and I put my x values in, and then my popped, it doesn't know what B and C is, so I have to decorate it so it pulls it apart. Another way to think about this is I could do popped 0. The first one is A, so I have to put that in my function. Then B, and then C. So this is just another review of what popped, that decorator at the front, that star pulls that apart. So you don't have to type all those out. That's kind of convenient. And that's what I've done here. Like you can see, I'm putting my optimized parameters into my cosine function and labeling it as a fit right there. And there's another way to do it. And so I can create another data column and then calculate my sum of squared errors and also my MAPE value. My MAPE value is pretty good, 1.4% error when I use my estimate as far as a day, an hour of the sun rising. And my R squared value is pretty good too. And then here is minimizing the sum of squared errors with my function. Here I've defined the function again. I probably didn't need to do that, but I wanted it not necessarily A, B, and C, but pull those apart and minimize my sum of squared error, minimize that, my min function, and then I give it a guess, 318.17.5, and use my minimize. So hopefully that's illustrative in terms of 3 different ways of doing fitting with polyfit, polynomials, with Scipy's CurveFit, where you can define a function, and Scipy minimize, where you define a function and your error function. And last, we're just going to talk about interpolation quickly. So sometimes you'll see tables like this. Here we have saturated water temperature table, where we have temperature of the water and the pressure of that saturated water. And what is the pressure at 23.2, for example? Well, that's interpolation. You're not necessarily you're fitting some relationship between the data points to be able to get what that 23.2 value is. And there's linear fits, so you just draw a line basically between these two, and that's this interp 1D. That's a linear fit from Scipy's interpolate. Or you can kind of use the data before and after it and estimate a curve, and that's that barycentric interpolator. Add some more curvature. And so, for instance, the vapor pressure at 18.2, right in between here. Gives 2.11 kilopascals when I do it linearly, and when I use the polynomial or the curved fit, it's 2.08, so it's slightly different. You'd expect that, as the linear doesn't include the other values where barycentric does. So I've typed in that table, and then you just put the table values in right there for interp and for barycentric interpolator. Put the table values in, the x's and y's per se, and then you just refer to that. It's a function, and you type the function and the function value, the independent value, and it will return you your interpolated value. Yeah, and you wouldn't want to get something weird where when you put in your interpolator, you get a different answer than what's in the table. So I just show that here. For the different interpolation values in the table, these should all be the same, which they are. So make sure to do that with your barycentric interpolator, and of course with your linear interpolator. God lives and loves us. Hope you have a great day.